strength. So your 5 main different compounds to be looking at. First one is network covalent solids or covalent compounds. Something we probably didn't address a lot last year. There isn't a whole lot to it this year. But what you'll see in the network covalent compounds is usually they'll give you a silicon compound, like silicon dioxide. Diamond, of course, is one of them. They form a nice network of shared electrons, and they're very typically strong bonds. Ionic, we've covered a lot in terms of it's a salt. It's going to, follow the charge distance idea in terms of its strength. Metallic, I'm going to talk about in just a minute. Polar covalent, it'd be, like your dipole-dipole hydrogen bonding ones. And then covalent is just regular nonpolar stuff, okay? So that's usually your London dispersion, your weakest forces there. But just so you can get an idea of what network covalent means, okay? In the diamond, it's just like one big long string of carbons. But they are bonded at angles, and they really provide a lot of strength because of their geometric angles of their bonding. The silicon dioxide here, same idea, forming this geometric shape, okay? Silicon carbide is another one that they sometimes, and usually you'll give you a multiple choice with 5 things in there, and one of them's a network covalent, and that's usually the strongest, that would be the one you would want to pick there, okay? So that's what we think of when we think of network covalent. Ionic, you're looking at your typical lattice structure here, crystalline, positive, negative, and it's very strong Coulomb attraction there between the positives and negatives, okay? Now the third one, the metallic, you probably, I know we don't cover it very much either. It's really these positive centers of the metal ions. The electrons are delocalized. They can travel around, and that's what makes them very good conductors of electricity, okay? So the electrons aren't really in fixed positions with certain atoms. They're kind of around the entire sheet of metal, okay? So they have those delocalized ability, and it does provide a lot of strength, okay? And we'll talk about, in terms of comparing metallic bonds to other metallic bonds, what makes them stronger in just a moment, okay? But here you're looking at, these are delocalized. They are not in fixed position around only certain atoms. They can travel around, and that makes them, do that photoelectric effect and also the conducting electricity very well. Now, I gave this to you already in your notes, so you don't have to write it down. This is how you rank them. Network covalence will always be the strongest. And in a multiple choice problem, they will give you one, and usually it's a silicon something or other, okay? Just so you know. They could give you diamond, of course, that one's very strong. Ionics are next, and then you need to go to looking at the charge, looking at the distance, the size of the radius, okay? Metallics will be after ionic in terms of strength. Then polar covalent with hydrogen, polar covalent with dipole-dipole, and then nonpolar covalent. With the London dispersions, more electrons make them stronger, okay? So bigger is better in the nonpolar covalent. Now, if we're looking at this particular problem where they did give us the melting points, what do we go by here? Who's stronger? Sodium fluoride, why? A higher melting point suggests what about its forces or bonds? Stronger bonds and forces holding it together. Very good. So, and in this particular case, since they're both ionic compounds, what's making the difference here as to why sodium fluoride is stronger than sodium chloride? What about the lattice energy? Fluorine is a smaller radius, smaller atom, so its distance is going to be smaller. That denominator part is now going to be smaller, so therefore your lattice energy is going to be greater, okay? So smaller the ions, the closer they get packed together, the stronger the force of attraction. Okay? So keep that in mind when you're looking here. That's really the only difference because they're both +1, -1. The charges do not change in these two compounds. So the numerator factor of the equation isn't really changing at all. Okay, it's the denominator, that radius, that distance, that's making a big deal. Okay? Now let's look at this guy. Whoa, big difference. Look at that melting point of magnesium oxide. 2852. That's pretty strong in terms of its strength and holding it together. Super high melting point. Fluoride is smaller than oxide, but magnesium is smaller than sodium. So the sizes are pretty generally the same. Oxygen and fluorine are pretty comparable. Sodium and magnesium are pretty comparable. What's the big changing difference here? Ion charges are different. Magnesium oxide are +2, -2. So the magnitude of the charges is much greater. So that numerator number is now much higher. And it's going to affect the strength, being able to break it apart. Okay? So thinking back to that. Okay? So sodium fluoride +1, -1, but magnesium oxide is +2, -2. That numerator value now will be much greater. Okay? So going back to Coulomb's law, which is sort of like the lattice energy, it's pretty close. Okay? But these are the two facts that you really want to make sure that you get down. The closer oppositely charged particles are, the stronger the attraction. So that's about the radius distance, how close they are packed to each other. The greater the charge, okay, the stronger the attraction. Those are the two main facts that you need to make sure that you write down. I mean, don't really need to write down all the big words up there. The magnitude of the electrostatic force of interaction between 2-point charges. Okay, what all that's saying is bigger the charge, higher the numerator. The closer you're packed, the smaller the denominator. The magnitude of your force is going to be a lot higher. And like I said, the Coulomb's law looks very similar to the lattice energy, except for its measuring force here of attraction. Okay, and probably didn't say this enough about Coulomb attractions. Are the electrostatic force, those positive negatives attracting to one another? So that is another attractive force to add to all of the other ones, the ionic bonding, metallic bonding, network covalent bonding. Your intermolecular forces are an attractive force. So the Coulombic attraction is also another force pulling things together, and you see that a lot in the redox reactions. Okay. So as you'll see, the equation's very similar to the lattice energy one, except for we're dealing with a force, and you don't really have to know the equation and be able to calculate with the equation. What you need to know about the equation is this charge value on top greater? Okay. Is the distance value smaller, so that you can tell ionic solids in terms of their forces? So you can have a list of ionic solids and be able to qualitatively decide who is stronger, basically. So they're not actually going to give you numbers and say plug them in and know this equation. You just need to be able to be able to tell me, yes, is sodium chloride stronger than magnesium oxide? Okay, and you would need to rank them, or you would need to be able to pull out of a 5-question multiple, 5-answer multiple choice question who's the strongest based off of this relationship. A numerator affected by the charge value, the denominator is affected by the distance and how tightly packed the atoms are in terms of their radii. Okay? So keep that in mind. Now the strengths of metals. Basically the same as ionic bonds. Smaller the radius, the more tightly packed they are, and usually the stronger the structure. So if you're comparing two metals in terms of their strength, usually the smaller radii is going to give you the stronger metal. Okay? So there you have that one. That one's a pretty easy trend to follow. Okay? And last but not least here, comparing the strengths of covalence. Polar is usually stronger than nonpolar, but there's always exceptions. Really big nonpolar molecule can be stronger than a very small polar molecule. So the general trends go in this direction. Polar with hydrogen bonding is usually the strongest, then polar without hydrogen bonding, and then nonpolar, which is going to be your London dispersion forces. And this would be your dipole forces. Okay? But there's always exceptions. And you have an example on the back to look at about a certain exception. So this is where you have to apply your conceptual knowledge to be able to figure it out. Like on the back it says, iodine is a solid at room temperature. Water is a liquid at room temperature. Who has the stronger force and why? So let's think about that. Why could that happen? Why would iodine be a solid and water would be a liquid? Iodine is nonpolar. It only has London dispersion. Okay? So think about that for a second. So let's regroup here. Why is I2 a solid at room temperature but water is a liquid? That would imply that I2 has a stronger force. Why would its force be stronger? Okay, so between these two there's 126 electrons, right? Right. Whereas our nice little water, there's only 8 electrons in between them, so this really actually can't even, in terms of size, it would be more like a little speck. That would be your water size, okay? So the sheer size of the idea that iodine is so much bigger kind of trumps the hydrogen bonding. So it's kind of, like you have huge London dispersion forces, and you have tiny little hydrogen bonds over here. Okay? So it wouldn't, therefore, you can have exceptions like that, where because water is so tiny in comparison of a molecule size, that even though it has the nice hydrogen bonding, it's not going to be stronger than something with a big, huge cloud that's going to create a huge temporary dipole. Okay? So sheer size alone can affect it, but conceptually think about that. Okay, so if they're telling me something I know is nonpolar is a solid, and this other thing that is polar is a liquid, I know that the reason why the London dispersion force one is going to be greater is because it's bigger, because that's the only thing that makes London dispersion forces greater. Okay? Does everybody get that? Now your job is to look at the series below, okay, and rank them.
Oh, this one's the strongest. I'm right here.
So what you should probably do is separate them into their categories, okay, and line them up that way. So if you look at, you have network, covalent, compounds, any network covalent compounds.
Oh, what we gotta do?
SiO2, good. What about compounds. Li2O, good. What? K, F, KCl. What about metals? And polar covalence with hydrogen bonding. Anything up there polar covalent with hydrogen bonding? H3, good. That's H having bond, yes. Okay, and now we have just polar covalence, no H bonding. Anything polar up there that's not having hydrogen bonding? Actually, C3H8 is propane, and it is quite nonpolar. Because it would be 3 C's and then 8 H's, like so. So very symmetrical.
H2S.
H2S definitely is going to be one of these bent shapes, like so. So H2S is, and then our nonpolar covalent C3H8 and CH4. Another thing to identify about these guys automatically that are going to tell you they're pretty much nonpolar is that they're hydrocarbons. Hydrocarbons are always going to be, when it's just that, these are called alkanes. Hydrocarbons, they're always nonpolar. So, from here, now that you have everything classified, now you can start ranking them. Who's the strongest? SiO2, good. Because it's network covalent, we're going to say it's the strongest. Okay, then, out of our ionic compounds, who's the strongest? Why? This one has a +2 with a -1, so it's going to have a greater charge value. What about KF and KCl? F is smaller, so it's going to be stronger. KF is stronger. Then KCl, good. Out of our two metals, who's the stronger one?
It's bigger. It's bigger. Oh.
Why zinc? Zinc has a smaller radius, so it should be stronger.
I don't even know where cesium is.
Cesium is strong here at the alkali metal.
Oh, there it is. Oh.
Okay. And since we only have one hydrogen bonding one, that's going to come next. One polar covalent, that's easy. Out of these two last two, who's stronger? C3H8Y. Well, it's bigger, has more electrons, bigger electron cloud, more London dispersion force. Really about the size and the electron cloud, not about the bonds.
I'm not tired.